Hello again, everybody. Welcome back. I'm back again. Um, Hope everybody's okay. Today, quite a short lesson, I hope, and quite a short piece of work to go with it. I want to cover the idea of nuclear equations. It's just a little skill, and once you understand it, you can apply it very easily to any kind of question that Cambridge can throw at you. Above my head is the important information I want you to take away as usual. Basically, three bits of important information. In red, I've written the term for an alpha particle. In green, beta particle. In blue, gamma ray. They're the three types of radioactivity. Down here underneath the symbol for alpha, I've just written a slightly different way of writing the term for an alpha particle. You can write it the same, but as He. I'll explain why as we go along. It should become fairly obvious, actually. Okay. When we talk about nuclear equations, the first thing you're going to need is a periodic table. I've got my Cambridge periodic table here. I'll send you one when I post this video. Cambridge has done something that I find quite confusing recently, actually. In the past, they've always put the large number that comes with the periodic table on the top and the small number on the bottom on each square of the periodic table. In the latest version of the syllabus, they've switched it around so the small number goes on the top and the big number is on the bottom. I find that a bit confusing. It's the same information, but just be aware of that. I'll explain why I think the big number should be on the top, the small number should be on the bottom in a minute. And when I send you a periodic table, I'll make sure it's that way around. Okay, so when you look at the periodic table, you can get all kinds of information from each box on the periodic table. If you're a chemist, you're interested in the electrons whizzing around the outside of the nucleus. Because we're physicists, we're only really interested in the nucleus itself. So the information I'm going to show you is what we can tell about the nucleus of the atom from the information that's provided on the periodic table. Okay, so here's a box that I've just pasted from the periodic table. There's three bits of information there that you can see. The first bit of information here is the symbol of the element. In this case, it's U for uranium. This is uranium-238, for obvious reasons. The other two bits of information are two numbers. First number, if you're a chemist, you call it the mass number. If you're a physicist, as we are, we're going to call it the nucleon number. It doesn't matter which term you use, they're both correct. I'm going to stick to the term nucleon number. What this piece of the periodic table tells me is that in uranium there are 238 nucleons. Nucleons are particles inside the nucleus which you already know are protons and neutrons. So therefore I know if I added together the number of protons and neutrons in the uranium nucleus, I would get 238 of them in total. Okay. The bottom number, if you're a chemist again, you'd probably call it the atomic number. I'm going to call it the proton number. That's the physics term for it. It's easy to understand what the proton number is. It just tells us the total number of protons. So I know in uranium there are 92 protons. Okay. If I want to find out the number of neutrons, you might have realized this already, you can just subtract the proton number from the nucleon number. You're subtracting the protons, so what's left must be neutrons. So if there are 92 protons, there are 238 minus 92 neutrons, which without a calculator I make as 146 neutrons. Okay. The thing that tells you what the atom is always the proton number. So when we look at the proton number when we look at the periodic table, to identify an atom, the thing we're interested in is the smaller of the two numbers. Okay, all right, moving on. Let's look at three types of nuclear equation. Okay, so we've seen this already, it's uranium-238. Uranium-238 is an alpha particle emitter, which means to try to become stable, it loses an alpha particle from its nucleus. The reasons why that is, you don't need to know. Some atoms are alpha emitters, other identifiable atoms are beta emitters. They won't do both. They'll do one or the other. The thing that actually determines which they do is the ratio of protons to neutrons, but we don't need to really know about that. Okay, so I'm going to show you how to do a nuclear equation for uranium. I've told you already that it's a alpha particle emitter, so it's going to be minus an alpha particle. I'll write it this way. So uranium-238 minus alpha particle. We know that the numbers on the alpha particle are, you can see above my head, 4, 2. And you've probably also realised by now what those numbers mean. It means that an alpha particle is made of 4 nucleons in total, and it's got 2 protons. 4 minus 2 is 2, so what that means is 2 protons and 4 minus 2 neutrons, 2 neutrons. We've already described an alpha particle as a particle made up of 2 protons and 2 neutrons. The next bit is easy. 238 minus 4 nucleons leaves you 2, 3, 4 nucleons for the nucleon number. 92 minus 2 is 90. Okay, that's it. The only thing that's missing is to identify what atom this is now. I should have mentioned in the previous video, and I forgot really. When something is radioactive, unstable, and wants to become stable, we said it does that by spitting out parts of its nucleus. If your nucleus has changed, you've become a different atom. So whatever this has become now is not uranium anymore, it's something else. To find out what that is, you take your Cambridge periodic table. The number we're interested in is not 234, it's the number 90, because that's the proton number. And I already said that what determines what an atom is its proton number. So if I look at the periodic table, I can see that the element with a proton number of 90 is TH, thorium. Okay, so that's the nuclear equation for an alpha particle emission from uranium-238. Uranium-238 becomes stable by losing an alpha particle and then becomes thorium-234. Okay. Thorium itself, I've written thorium-90 here, I should have written thorium-234. Thorium is a beta particle emitter. So now we can move on to our next equation. Here's thorium, thorium-234. It's a beta particle emitter. This is a bit harder to understand than alpha. It's going to be minus beta. And you can see that the numbers for beta are 0 nucleons and minus 1 for a proton number. It's not that easy to understand, but you probably understand already. Because beta particle is an electron, it's not a nucleon, it's got 0 nucleons. And because when you lose a beta particle, a neutron becomes a proton, we need the proton number to increase by 1. Minus 1 is the same as plus 1. So therefore it's going to increase by 1 to represent the gain in a proton in the nucleus. I hope that made sense. Okay, 234 minus 0 is 234. 90 minus 1 is 91. Okay, again, the number we're interested in here is the proton number, 91. So I get my periodic table, I look in the periodic table again, and I can see that the element with a proton number of 91 is Pa, which I believe is protactinium. Okay, so that's our nuclear equation for a beta particle emission from thorium-234. Thorium-234 loses a beta particle and becomes protactinium-234. Okay, hope that made sense. And then finally, I've got here a atom that releases gamma rays. This is cobalt-60. This is by far the easiest one to understand. So cobalt-60 becomes stable by losing a gamma ray. Gamma ray is not a particle, so therefore it has 0 nucleons, 0 protons. We don't need a calculator for this one. 60 minus 0 is 60. 27 minus 0 is 27. And therefore, I don't need to even look this up in the periodic table. I know that the element with a proton number of 27 is still cobalt. It's just cobalt-60 with less energy in the nucleus, so therefore it's more stable. So that's by far the easiest type of equation to do. Okay, that's it, I think. Just to return to why I said that alpha parts can be written as the symbol alpha or the symbol He. On the periodic table, you'll see that 4,2 is exactly the same as a nucleus of helium would have. So therefore, an alpha particle is also referred to sometimes as a helium nucleus. And that's the reason why we use the symbol He sometimes. Okay, that's it from me. There's some work to follow. I'm just going to give you some atoms, and I'll tell you what kind of emitters they are, and you can work, and I'll send you a periodic table, and you can work out and show me the nuclear equations for what these things become. It should be a very simple and very straightforward piece of work. Obviously, go back through the video if some of it didn't make sense. Hopefully, most of it did. Pause it on the equations if you like, if that makes more sense. Before I go, I'll just to make sure that obviously you don't need to memorize the periodic table. If you get questions on, sometimes they come up on a multiple choice test on your exams. They'll always give you a periodic table. Just be aware of which is the nucleon number and which is the proton number on your periodic table. Also, Cambridge will never expect you to memorize which type of emitter each atom is. They'll always tell you this is cobalt-60, this is a gamma emitter, or this is thorium-234, this is a beta emitter, etc. So don't worry about that. All you need to take away from this lesson is the skill of turning one atom into another atom after it's emitted either alpha, beta, or gamma. One thing you're going to have to learn, though, actually, is the numbers for each type. So alpha 4,2, beta 0, -1, gamma obviously 0, 0. Okay, get in touch with me if you need any more help. That's the lesson for today. Okay, thanks very much for your attention. Take care of yourselves and your family and each other. Hopefully see you in a few weeks' time. Okay, goodbye.